All right, welcome back to our second day of our Unit 2 on atomic theory. So today we are going to be exploring some of the basic particles that make up all atoms and matter in the universe. So let's go ahead and get started. I'm going to start off sharing my screen here. And we're in Canvas chemistry. And so remember, on the Bitmoji pages, you want to be in atomic theory. I have not opened up these other ones for us yet. All right, when you zip over here to our main page on atomic theory, last time we did identify physical and chemical characteristics of a substance. Today, we're going to define the characteristics of the three fundamental particles, as well as their mass, charge, and location. We're also going to calculate the mass of an atom. So let's get going. So I'm going to hit number 2, particles and isotopes. And again, there is a set there's a Google Doc here for you to complete. And remember to add this to your e-binder. All right. So all matter is made up of particles. And the most fundamental particle that we have are atoms. They are the smallest indivisible particles that still have the characteristics of that particular substance. So let's go back and look at this. So from last time, we know that all matter is made of atoms, okay? Atoms, they are small. They are representative of 118 different elements. So things like that you may have heard of: hydrogen and carbon and gold and silver, lithium. There are 118 different ones. And if we separate down to the smallest particle we can go of lithium, we have one atom of lithium. If we divide that further, yes, we can, but then we don't have lithium anymore. If we have gold, we can separate gold particles and gold atoms from other gold atoms until we end up with one gold atom. And that is as small as we can go. If we go smaller, take that apart, we end up with subatomic, that's where that word comes from, particles. So all matter is made of atoms. Okay, atoms, number 2, are made of 3 fundamental particles: protons, neutrons, and electrons. The first particle is the proton. Properties of the proton: its mass is just one AMU, atomic mass unit. The charge is +1. And its location is in the nucleus at the center of the atom. The second particle, the neutron, okay, its mass is the same as the proton, 1 atomic mass unit. It does not have a charge, it is neutral. So you might remember that, neutral and neutron. And its location is right beside the protons in the center of the atom. They're the only 2 that are inside the atom. The third particle is the electron. These are very, very small little things that fly about outside the nucleus. So their location outside the nucleus. Their mass is so small that for all practical purposes, we say it is 0. It's really, if you went back and Googled it, you would see that it would take about 1,000 electrons to equal 1 proton. And so therefore they are so small that we just say they are 0. So we don't count them when we're calculating mass. Their charge is -1. All right, number 6, the number of blank is equal to the atomic number of the element. Well, what I've done for you is I have tried to make the Bitmoji world easy. And so I have put together a periodic table, and in the periodic table, you can see these numbers across the top, that iron is 26, calcium is number 20, sodium is number 11, lithium number 3, hydrogen number 1. These are the atomic numbers, and that number tells us the number of protons. It never, ever, ever changes. If it has 3 protons, it is lithium. It can't be anything else. The number of neutrons and the number of electrons can change, but not the number of protons. So let me go back over to our main sheet here. The number of protons, okay, in number 6, is equal to the atomic number of the element. The number of protons determines the element. So again, if it has 3 protons, it is lithium. If it has 6 protons, it is carbon. We know that automatically. This number never changes. Atomic mass is equal to the number of protons plus the number of neutrons. We just add those two together. So in lithium, if I have 3 protons and 4 neutrons, I just add those together. 3 plus 4 is 7. 7 atomic mass units, whole numbers, easy math. So an example of this would be lithium that has 3 protons. We know that because we looked it up on our periodic table. Remember that lithium has 3 protons. And if it has 4 neutrons and 2 electrons, well, we're going to take 3 plus 4 is 7. And we don't count the 2 electrons because they have no mass. So it's 3 plus 4, the mass is 7. All right, we have a special circumstance in this thing called isotopes. And so I'm going to do a different share screen here and show you a whiteboard so that we can talk about some elements. And so if I have the element carbon, and carbon has 6 protons, okay, and we know that because that's its atomic number. And I'm just going to make one up here because the number of neutrons could be 4, 5, 6, 7, 8, because it changes. Different carbon atoms have different numbers of neutrons. So I'm going to say, to start off with, this one has 6 neutrons. I'm not going to talk about electrons. And so our mass right now is equal to 12, the number of protons plus the number of neutrons. Okay. Now, if I have a second carbon atom, it absolutely must have 6, that's a terrible 6, but 6 protons. Number of neutrons. I think this one will look like the other one, 6. So it has a mass also of 12. I'm going to make a third carbon atom. Protons has to be 6. It's always 6. And this time the number of neutrons is going to be different. This one is going to have 8 neutrons. Why? Because they exist out there in the real world. And so 6 plus 8 is 14. All right. In this group of 3 atoms, carbon atoms that I've done, these 2 are both carbon atoms, but they have the same mass. Okay. They are not different. Okay. These 2, they have the same number of protons, but a different number of neutrons. And so this little group, I'm going to do it this way so that this is an isotope. This pair of carbon atoms are isotopes of each other. So the definition of an isotope is same element, different numbers of neutrons, and so they have a different atomic mass. This over here is not an isotope pair, not an isotope. And the reason is that they both have the same mass because they both have the same number of neutrons and the same number of protons. So this is not an isotope, while this group over here is an isotope. All right. So this one is an isotope. We'll put that wording back in there. These are isotopes. So you'll need to remember that word, isotopes. All right. So that is, but all of this writing that we did here, I would like it if we could do that a little bit differently. I'm going to go back here one more time to my whiteboard and write this a little bit differently because this is a lot of writing. Chemists like to write things in shorthand. So what I'm going to do is I'm going to take that 6 protons and I'm going to put it right here down at the lower left corner. And I'll just put a little P down here so that you can remember that's protons. Up at the top, I'm going to put its mass, 12. And remember, if we know the mass, we can calculate the protons because 12 minus 6 would be 6 neutrons. So 6 protons, mass of 12. And so now I could write our third one the same way. Well, it's still carbon, so it has 6 protons, but it has a mass of 14 atomic mass units. So I know that the number of neutrons is 8, and this pair is an isotope pair. Okay, so these two are isotopes, and they are isotopes because they are the same element, but they have different atomic masses. All right, so if I go back over to our other screen, and I'm giving you some of these. So our notation at the lower left, I've diagrammed this for you, is the atomic number or the number of protons. Ni is nickel. Upper left, mass is equal to protons plus neutrons. So if I subtract these two, I would get the number of neutrons, in this case 32. Charges up here, we'll deal with that one later. So in the lower left is number of protons or atomic number. Upper left is the mass. Upper right is the charge. So now I've given you 3 isotope notations, and I want you to figure out which is which. So boron, this one, always has 5 protons and a mass of 12. So 5 protons and a mass of 12, that's the third one. Vanadium has 23 protons and a mass of 46. So that's this one, 23 protons and a mass of 46. Silicon, again, protons here, mass up here, so 14 and 30. So 14 and 30, that's the second one, 14 protons, mass of 30. Okay, an isotope of boron noted above. Well, if it's an isotope of boron, it still is boron. It's got to have 5 protons. But this number up here, the mass would have to be different. So 511, 513, 514, 510, any of those would work. So let's see what we have. 5,6 would work because that would be 11. 5,7, let's see, 5 plus 7 is 12. Whoops, that one would not work because that's the one we already have. All right, so the second one is not an isotope. 5,8, that'd be a mass of 13, and 5,12, that'd be 17 for a mass. All of those would work except for the second one because it would be the same boron as I already wrote. 2 isotopes of lithium. Okay, lithium always has 3 protons. It has to be, the isotopes have to have the same number of protons. It has to be the same element. So I'm going to compare these 2 atoms. The first atom has 3 protons, the second one has 4. These cannot be isotopes. Their protons are different. Okay, the second one, protons are the same, 4 and 4. Let's check neutrons, 3 and 3. They're the same. Okay, mass of 7 for both of them, not isotopes. The number of neutrons must be different. And number 3, 5 and 5, good. The protons match. 3 and 4, the neutrons do not match. That's an isotope pair. Atom 1 and atom 2 are isotopes. All right, we'll check the fourth one, 4 protons, 5 protons. No, that's not going to work because they are not the same element. So there's only one in here that represents an isotope pair. Which 2 particles are inside the atom? I would hope you'd say protons and neutrons. And isotopes can be different elements as long as the number of neutrons are different. Can isotopes be different elements? No, they cannot. They must be the same element. So that one is false. So what I want you to do here is just fill this table in. Okay, I'll leave that for you to do. And then I want you to write the isotope notation for each of these. And by isotope notation, what I mean is like this. Don't worry about the charges, okay? I've given you charges. If you figure that one out, that's okay, but you don't need to, all right? And that's your assignment. So working on isotopes, things that have the same atomic number, same number of protons, but different masses.